For most of modern cosmology, the universe had a script. Space expanded. Galaxies drifted apart. The dark between clusters widened, like a wound that would never close. And behind that widening stood dark energy, the invisible component believed to make up about 68% of the universe's mass energy budget. The force tied to the shocking 1998 discovery that cosmic expansion is accelerating. In the standard model, Lambda CDM dark energy is treated as a constant. It does not fade. It does not turn. It simply keeps pushing. If that picture is true, the universe does not die in fire or collapse. It dies by dilution. Stars burn out, galaxies vanish beyond each other's horizons, and everything ends in an endless frozen separation. But in March 2025, that certainty took a hit. The DESI collaboration released a new analysis built from its first 3 years of survey data, covering nearly 15 million galaxies and quasars, in the largest 3D map of the universe ever assembled. On its own, DESI could still live inside the standard model. But once researchers combined that map with the cosmic microwave background, Type 1, supernovae and weak lensing data, the fit began to shift. The model that looked cleaner was no longer the one with constant dark energy. It was the one where dark energy changes over time, possibly weakening. Depending on which data sets were combined, the tension with the old picture rose to roughly 2.8 to 4.2 sigma, not a discovery, but far too loud to dismiss as background noise. Then came the southern sky. In January 2026, the Dark Energy Survey's Year 6 Cosmology release brought in the weight of a full 6-year campaign, a dataset spanning about 5,000 square degrees and 669 million cataloged objects, with its core cosmology analysis, built from galaxy clustering and weak gravitational lensing across the final survey. Its results did not kill Lambda CDM, but they narrowed the room around it. And once 2 major dark energy observatories, one in Arizona and one in Chile, started hinting in the same direction, an old ending returned from exile. The universe might not expand forever. It might be slowing toward hesitation. And somewhere beyond that hesitation waits the possibility physics tried to bury the big crunch. To understand why that possibility is so disturbing, the reporting has to move from telescopes to the underlying rule they are testing. In the standard picture, dark energy behaves like a cosmological constant, a fixed pressure built into space itself. It keeps the cosmic scale factor accelerating outward, no matter how much ordinary matter thins out. But the recent DESI analyses point toward something less stable, a form of dark energy, whose influence may have been stronger in the past and weaker more recently. That is why cosmologists keep circling the same phrase, evolving dark energy. It does not sound violent. It sounds technical. But in practice, it means the engine that was supposed to keep the universe opening forever may be losing thrust while the universe is still in flight. That change matters because expansion is not a one-way event. It is a contest. Dark energy pushes outward. Matter and dark matter pull inward through gravity. For decades, the outward side seemed decisively ahead. The 1998 discovery of accelerated expansion pushed the big crunch to the margins, almost into retirement. But if dark energy is not constant, then the old ending re-enters the room. The latest DESI results track dark energy's effect across roughly 11 billion years of cosmic history, and the pattern emerging from combinations of DESI supernova CMB and lensing data is exactly the pattern that makes theorists uneasy. Not stronger acceleration forever, but a universe whose late-time future may depend on how quickly that invisible pressure decays. This is where the fear stops being abstract. If the repulsive side weakens enough, expansion slows. If it slows far enough, it reaches a maximum size. After that, the sign of the future flips. Space does not just expand more slowly. Space begins to contract. In the model explored by Hoang Nan, Liu Yu Cheng Chu, and S.H. Henry Tye, the data can be fit by an ultralight axion dark energy scenario, plus a negative cosmological constant. In that case, the universe keeps expanding for about 11 billion more years, reaches its largest size, and then reverses. The total lifespan comes out to about 33 billion years, leaving roughly 20 billion years before a final collapse. Not a freeze, not a fade, a cosmic rollback toward a terminal point. If that model is right, the most important moment in the future of the universe is not the final collapse. It is the silent turning point before it. According to the Cornell analysis built on the recent dark energy results, the cosmos would continue expanding for roughly another 11 billion years, reaching a maximum size about 69% larger than it is now. That sounds like distance, not danger. But in cosmology, that is the instant the entire direction of reality changes. For billions of years, every large-scale structure has lived inside a universe that stretches. In a big crunch scenario, the stretch stops, the scale factor peaks, and then the geometry of space itself begins to reverse. The universe does not simply become old, it begins to come back. That reversal is what makes the threat so absolute. A collapsing universe is not a local catastrophe moving through space like a wave or an explosion. It is space changing its mind everywhere. The same framework that once increased the gulf between galaxies begins to reduce it. Gravity, helped by weakening dark energy or a negative cosmological constant in the model, stops losing the tug-of-war and starts winning it. This is why the recent hints matter so much. DESI's 3-year map, when combined with supernova CMB and lensing data, points toward dark energy that may evolve with time rather than remain fixed. DES Year 6 tightened the late universe measurements across 6 years of observations, leaving cosmologists with a picture that is still consistent with Lambda CDM but no longer comfortably secured by it. The danger is not that collapse has been proven. The danger is that collapse is back inside the allowed physics. And once contraction begins, there is no protected scale. Galaxies, clusters, radiation backgrounds, the thermal history of the cosmos. Everything starts moving toward higher density, higher temperature, and a future with less room than the past. The universe that once seemed committed to endless escape would instead reveal that its expansion was only a phase. A long one, a majestic one, but still temporary. In that reading, the greatest hidden danger in dark energy is not that it drives the universe apart forever. It is that it may have only been delaying the moment when everything turns around. But this is where the story becomes more dangerous, not less. Because the possible return of the Big Crunch is not emerging from a clean, unanimous verdict. It is emerging from a fracture line in the data itself. DESI's 3-year baryon acoustic oscillation results show the strongest pull toward evolving dark energy, only when they are combined with other probes, especially Type 1a supernova catalogs. And that is exactly where the argument turns sharp. The preference for dynamical dark energy can range from about 2.8 to 4.2 sigma, depending on which supernova sample is used. In the formal DESY6 combined analysis, the result in a simple WCDM extension still shows no significant preference over Lambda CDM, even while the overall late universe constraints become tighter than ever. That means the universe is not yet confessing. It is only beginning to contradict itself. That uncertainty is not a minor technical footnote. It is the hidden danger inside the entire claim. George F. Stethio's analysis argued that the evolving dark energy signal is strongly dependent on the supernova compilation and may be vulnerable to low redshift versus high redshift calibration offsets, small enough to sound harmless, but large enough to erase the need for new dark energy physics. In other words, one of the most unsettling possibilities in cosmology may be either the first crack in the standard model or a mirage caused by how cosmic candles are stitched together across distance and time. The threat is not only that the universe may collapse. The threat is that right now, humanity cannot yet tell whether it is seeing new physics or the limits of its own measurements. And that is why the next few years matter so much. Euclid's first major cosmology data release is scheduled for October 21, 2026. Rubin Observatory already revealed its first images on June 23, 2025 and began demonstrating its high-cadence sky monitoring power in early 2026. NASA says Roman is now fully assembled and could launch as early as fall 2026 with dark energy as one of its core science targets. 3 new judges are stepping into the room. If they confirm the pattern, the Big Crunch stops being an old discarded ending and becomes a live forecast for the universe itself. So the final implication is not that cosmology has suddenly proved a coming collapse. It is that the universe may be far less committed to its current behavior than humanity assumed. DESI's latest results still stop short of a formal discovery, and the standard Lambda CDM model still survives. But the survival is no longer serene. The old picture said dark energy would keep driving expansion forever. The new hints say that force may evolve, weaken, and eventually give gravity a second chance. That is why this story has unsettled so many physicists and science outlets. It does not merely tweak a parameter. It reopens the question of how the universe ends. If the weakening is modest, the cosmos could still drift toward a deep freeze. If it is stronger, or tied to something like an ultralight axion field, plus a negative cosmological constant, then expansion becomes temporary, a long outward breath before a reversal. In the Cornell linked model, built from these new data trends, the universe expands for roughly another 11 billion years, reaches a maximum scale around 69% larger than today, and then contracts, ending in a big crunch after a total lifetime of about 33 billion years. Other models leave the timetable looser, but the emotional geometry is the same. The universe may not be escaping forever. It may only be buying time. That is why Euclid's October 21, 2026 cosmology release, Rubin's new sky survey era, and Roman's approach to launch matter so much. They are not just gathering prettier maps of galaxies. They are being asked a harder question: is the acceleration of the universe a permanent law or a phase that will end? Over the next few years, those observatories may either flatten this anomaly back into statistical noise or turn it into the biggest cosmological shift since 1998. And that is the most unsettling ending of all. Humanity may live in a universe whose greatest threat is not explosion, not chaos, but reversal. The stars, the void, the expansion itself, all of it may look like freedom, only because the collapse has not started yet.